This is number 42. Number 42 is basically asking us to identify whether we have a weak or strong acid. And if it is weak, we need to write an actual equilibrium expression. So I'm not going to go through all of these. I'm just going to look at part B and part C. And so part B looks at this molecule, HCHO2. And so this is formic acid. And so again, for my class, I want to reiterate that Tro likes to show you that acidic proton source by writing it first in the actual formula. Again, I want to reiterate that for how I tend to write these type of organic acids in lecture and on the exam is in this format. And again, we're trying to recognize that we have this CO2H. The CO2H, remember, is an important group for hydrogen bonding in chapter 12 and 11. And so we still want to recognize that group. In this case, it's the CO2H that's the acidic part. And so that's really our source of H plus, is that hydrogen on the right. So I apologize for any confusion. I just want you to know that this is how Tro writes his acids, making sure that that acidic hydrogen, that H plus source, is written first in the formula. I do that for inorganics, but for organics we have, again, I want this recognition of the CO2H. So organic acids, remember, that's our big distinction. They contain carbon, and so we have carbon in this structure. And while there are some exceptions, remember, these guys tend to be weak. And so if they're weak, then we have to write an equilibrium expression. And that is our equilibrium expression. We have the formic acid and water in equilibrium with what they would call formate and hydronium ion. So we have our acid, we have our base, these would be the parents, and then we have our conjugate base and our conjugate acid as a result of this equilibrium. And so from that equilibrium reaction, we can now draw an equilibrium equation with regards to Ka. And that would be just like from chapter 14, our products over our reactants. And so that's our equilibrium expression. This is our equilibrium reaction. Again, H2O does not appear in the equilibrium equation because it is a pure liquid. So that's part B. Again, organic acids tend to be weak, and so this will be the equilibrium expression and equation that we would use to solve for concentrations or Kas or pH. Now let's look at part C. Part C looks at sulfuric acid. And sulfuric acid is an inorganic acid. Right? And since it is inorganic, it lacks carbon. And so we have no carbon in the structure. And so for inorganic acids, both Tro and I agree, is that that H plus source is written first. So I apologize for the distinction, but inorganic acids, we write the H first, that's going to be the proton. For organic acids, I like to write that H as a CO2H. So we have inorganic acid here. And remember, inorganic acids tend to be strong. Now, there are some exceptions to the rule, but for the most part, these guys tend to be strong. And the reason why they're strong is because the conjugate is stable. And the one reason for us why this conjugate is going to be stable is enhanced resonance. And so if we look at sulfuric acid, again, we write the equilibrium very much the same. We have our acid, we have our water. Make sure our equation is balanced. And so this would be our equilibrium equation. That sulfuric acid reacts with actually two waters because there are two acidic protons to yield two hydronium ions and a sulfate. And so we're still balanced in charge. If we really look at this equilibrium, it's really very one-sided. Meaning the better way to draw our equilibrium arrow would be one that is like this. It's actually very favored to the product side. And the reason for that, again, is the stability of the sulfate anion. The conjugate, in this case base, is very stable because it has a lot of resonance. And so for this reason, sulfuric acid is strong. And so there really isn't an equilibrium constant expression for it. It simply dissociates to give you the amount of H3O plus in solution that you get from the stoichiometry of the sulfuric acid. That's number 42C.